Since our last test, we've been working with simple interest and compound interest. Now, what I'd like you to recall is the following. You know, if I have A is equal to P1 plus I to the N, that P here is our start value, also known as the present value. We have I, which represents the rate as a percentage per year, and N represents the years. You'll notice that we have, right now, we have a rate per year, and we also have the number of years. Based on this, every equation that we did in the last couple days looks something like this. Mr. S wants to put $2,000 into a bank account that pays 8% per year. Basically, every time we do these problems, we just basically had to start off by creating an equation. A is equal to 2,000, which is our start value. 1 plus I, which is the rate per year, which is 8%. But you recall 8% is the same as saying 0.08. And N is our year. Now you'll notice that this looks very similar to exponential equations. Notice I always remind you that the basic compound interest problem is very similar to our exponential equations we learned about last unit. Now, the next part of the question would be very simple. How much will there be after 15 years? Because N is the number of years that we were talking about up here. That means all we have to do is take our equation and substitute 15 for N. So we have A is equal to 2,000, 1 plus 0.08 raised to the 15. And we calculate our final answer being $6,344.34. And that's what we get for our final answer. Again, every time we do these problems, we always have to have some form of construction of our equation and then some form of substitution using what they've asked us for. The next few lessons will always deal with that. You'll note that today's lesson talked about different compounding numbers. So I'm actually going to zoom in on this chart that I've put on the right side here. You're eventually going to take a look at this and see what comes up. So here's what we're going to do. So when we talk about the compound name, we have all these different terms. We have annual, and when you hear something that is compounded annually, all we're relating to is the number of times in a year. That something happens. So if it's annual, the compounding number is 1. If I have something that is semi-annual, that happens twice a year. If I have something that's quarterly, that happens 4 times a year. Now, the next biggest compounding number is monthly. And how many times does that happen? You guessed it, 12. The next one that we have is biweekly. But we'll hold off on that first. We'll go and write up how many times something happens if it's weekly. If something happens when it's weekly, it's 52. So now we can go back exactly one step. Bi-weekly basically happens every 2 weeks. So it doesn't happen every week like before. It happens every 2 weeks. So essentially we're dividing by 2. So we have 26 weeks. And then we have daily, which is 365. So all of these things relate to the number of times in a year that something happens. Now, for every one of the problems that we work with, let's take a look at this problem that we have here. We're always going to have to bring out our apron. The moment you see something that talks about compounding, you're always going to bring out your apron. An apron refers to the following: all the variables that are used in the future value, or the amount of a compounding interest. Basically, let's go over this problem and we'll see how we use it. Mr. S wants to put $2,000 into a GIC account that pays 7% semi-annually. Now, first of all, we need to create an equation. So we'll bring out our apron, and here's what we know. If we look at that $2,000, that $2,000 is either the A value or the P value, the amount or the principal. So we look at that problem. We have $2,000 that's being put into a bank account right now. So we're going to immediately say that that is actually $2,000, and that represents the start value. So this represents P. The next thing we have to do is we have to figure out what the rate is. And essentially this is the rate. The rate R is going to be calculated as, well, 7, I always do this. I write 7 over 100, and I use my calculator to find my actual decimal percentage. Finally, this is the hard stuff. Anytime we talk about I, we have a specific equation that we use. We use R divided by the comp number. Now, the comp number is always tied to the comp name, which is semi-annually in this case. And if we go look at our chart over here, semi-annual means this happens twice a year, which means that this I value is 0.07 divided by 2. Now, I tend to leave this number as it is because sometimes these decimals don't come out nicely and you end up rounding. And in business, we tend not to want any rounding because when we round, we end up losing money in the end. But in this case, we'll do this just for this problem. The next problem is to figure out what n is. If something is compounded semi-annually, semi-annually means the number of times it happens within a certain number of years. So now we're going to actually write an equation for that. This is going to be years, so n is equal to the years. And then we times that by whatever the comp number is. Okay? So now, let's go to our equation, because it says here in this problem, it says we have to create our basic equation. Apron helped us find all the variables that we need for this following equation. A is equal to P1 plus I to the N. So we use our apron. Well, we don't know what A is, so we're going to leave A. We have P is 2000. We have 1 plus I, which is, in this case, for this specific problem, it comes out nicely for a decimal, so we'll just write 0.035. Raised to the N, and I'm going to leave N normally because right now I don't know what N is. And now what we'll do is we're going to calculate our final problem using our apron. So every time we know we've got a problem here, we're always going to start by setting up apron. We know that this is the problem and it happens after 15 years. So let's quickly set up apron and you'll see what our answer is. Now basically after we bring out our apron, we get the following. Now notice, N is equal to 15 times 2, which equals 30. So I always want to simplify what goes into my exponent. And then what I simply do is I substitute. And we get the following. In our basic equation, we start off with A is equal to P1 plus I to the N. And now we continue substituting directly, which is equal to 2000 bracket 1 plus, well, I won't put in 0.035 that we had here. I'll actually put it how I expect to see it in most of your work. 0.07, and then we divide by 2. Whatever you get for the I value goes there, wherever I is. And then we substitute our 30. When you do your final calculation, you're going to get $5,613.59 as our final answer. So that is what A is equal to, and I'm just going to put a box around it. Now, that's all you really need to know. The last thing that we have to talk about is what happens when we're talking about the exponential graph. So I'm going to basically just draw what's actually happening on our graph. So imagine this is our graph for our two exponential equations. I'm going to write them up over to the side here. One is going to be in blue and one will be in green. So our original equation, so imagine we had our original equation that we started with. A is equal to 2000, 1 plus 0.08 raised to the N. Now, if we were drawing this, you knew from our basic exponential laws that we learned a long time ago that this is a growing function, an exponential growing function with a starting value of 2000. And that starting value represents the y-intercept on my graph. So this portion represents the amount, and this represents the years. And what we're going to do, actually no, we're not going to represent the years. We're going to represent all of these with N on the bottom and amount on the side. Now, so this portion here is our starting value. So imagine that's 2000. If I was to graph this, I would have something that would look like this. It just starts off slowly, but increases quicker and quicker over time until finally it doubles, triples, and just continues on forever. Now, the next equation that we used today was A is equal to 2,000 1 plus, well, 0.07 divided by 2 is 0.35. 0.35. And we raise that to the n. Now, you'll note that this everything else is the same. The n value is the same, but the difference is our rates. In this case, our rate is lower. Now, because our rate's lower, it's going to start off slower, but eventually what will happen is, because it compounds at the same rate, eventually what happens is our numbers will eventually overtake each other over time. It's crazy how this works. You start off slow, but eventually they'll actually catch up to the lower one will catch up to the previous one, because essentially, if you think about this first equation was 8%, but this other one was 7%. The only difference is the number of times that this thing compounds in a year has increased from once a year to twice a year. And what happens is, it might start out slowly, but eventually it's going to catch up and be our intercept right here. And this will be our overtaking point. And then next thing you know, our blue graph will overtake and make more money over time, because the calculating period is double the amount compared to the original green one, if you think about it. So for this one, if I basically looked at it, imagine this was an 8-year description of what happens with the money, right? After 8 years, it just grows like this. But this one actually grows double that amount, because there are 16 different times where it compounds. And because of compounding, the compounding makes this thing grow like gangbusters. Now, your homework for today is the following. So I have a note online for you. I call it lesson 3. You're going to do number 8, number 2, 5 to 8, 11, 14, and 17. Now, all of those questions are very similar to what we did before. Good luck, kids.